Hello everyone, I'm Zhixing. We came from the National University of Defense Technology, and I'm excited to be here to share our work, vtism. Today, many services such as AI inference and big data application are increasing their memory usage. We need more memory capacity, lower latency, and higher bandwidth. However, DRAM remain costly, and servers are concentrated by limited DIMM slots and DDR pin counts. This restriction poses a serious barrier to scaling memory in traditional DRAM-based service. One promising solution to this problem is Compute Express Link (CXL). Traditional memory modules are attached to the CPU through a wide parallel protocol called DDR. In contrast, CXL device linked to CPU through PCIe protocol with high bandwidth. The CXL device shows like a non-CPU NUMA node but with cache coherence, and the CPU can easily use load or store instruction to access the CXL memory. Moreover, CXL supports multiple generations of DDR memory, which means that after the server upgrades its DDR, it can still use the old DDR on the CXL device, which greatly saves costs. To take advantages of this capacity, many servers machines choose to integrate fast local DRAM with large capacity CXL attached memory. However, although CXL can provide more memory capacity, it has higher access latency. In practice, CXL latency usually 2 times higher than local memory latency, and such high latency slows down popular cloud workloads. Therefore, to minimize slowdown, we need to place frequently accessed hot data to local memory and migrate cold data to CXL memory. Such data placement called memory tiering. Traditional memory tiering has 3 steps. First, we monitor memory access behavior and track the pages which has been accessed recently. Then we collect the data and classify pages to hot and cold. Finally, we migrate hot pages to fast local memory and migrate cold pages to slow CXL memory. There are many exciting work which run very well on bare metal environments, but they encounter additional constraints and do not work well on virtualization environments. So what's new challenges in virtualization environments? First is the semantic gap between host and guest. Virtual Machine Monitor (VMM) introduced an abstract layer that obscures the host visibility into the current application workload. The semantic gap between the host ability to perform memory management, particularly in page tracking and classification. For example, we start a 32 GB virtual machine. From host side, host can only see a VM progress with 32 GB, and it needs to scan the whole 32 GB area. But from the guest side, guest kernel knows exactly the memory usage area, which reduces the scanning range. Second, the host often misidentify page types due to limited access to the guest kernel module semantics. Page classification typically depends on the page cache information maintained within the guest OS, which is not accessible from the host. From host side, red line shows that the host considers all pages to be anonymous pages. In contrast, the guest kernel controls the exactly page cache information, and it can simply distinguish anonymous and failed pages in blue line. Linux kernel adopt different reclamation strategies for different page types, so it's important to get the right type. There are 4 common page tracking technologies, but not all of them are suitable for virtualization. Page fault-driven method trigger frequent VM exists, and page table sampling often gets inaccurate results, leading to suboptimal decisions. Hardware counter-based approaches such as PEBS are unreliable in virtualization environments. Given these limitations, we choose page table scanning as a practical compromise. This technology typically uses a fixed scan interval with the overhead background scanning. The scanning interval is concentrated to ensure that the impact on application performance less than 5%. But for diverse workload intensive in VM, it's impossible to choose a fixed scanning interval to fit all workloads. The frequency of page table scanning is influenced by 2 key factors. scanning time and scanning interval. The scanning interval is typically configured to mitigate the overall introduced by the scanning process, while the scanning time is directly determined by the number of active PTEs associated with the current running progress. To find the relationship with workload, intensity, and scanning time, we record benchmark variation in both active PTEs and scanning time duration. From the left picture, we can see that scanning time exhibits a strong correlation with active PTE items. Moreover, we designed a memory-intensive program to find the relationship between workload intensity with scanning time. The right picture reveals a positive correlation between active memory footpoint and scanning time, with about 4 to 5 milliseconds per gigabyte. This result indicates that higher memory access intensity leads to increased scanning time. We observed that the performance slowdown introduced by page table scanning is a nonlinear relationship with workload size. We measure the slowdown under varying workload intensities, while background page table scanning is performed at different fixed intervals. The runtime slowdown increased quadratically with active memory size. In addition, longer scanning intervals lead to lower performance slowdown. Our experiment findings yield two key conclusions. First, scanning time scales linearly with active memory workloads. Second, scanning time has a quadratic influence on application memory access performance. At higher workload intensity, the number of active PTEs also increase, thereby extending the duration of each scanning round. During the scanning, low-level operation including traversing the page table structure, modifying the access 30 bits, and flushing the corresponding TLB entry will finally influence the application performance. Since the fixed interval method is not good enough, vtism introduced an adaptive page table scanning strategy that dynamically adjusts the scanning interval based on the actual memory access activity. As described before, the performance slowdown caused by page table scanning exhibits a quadratic relationship with scanning time, where T-scan means the scanning time of the current round. K-scan and K-base are adjustment coefficients that control the sensitivity of the interval to scanning time. T-base is a lower bound that ensures periodical scanning under low activity. For lightweight workload, the scan frequency is increased to avoid wasting CPU cycle. For heavyweight workloads, the scan frequency will be controlled. We use experiment to find the best suitable parameters as the yellow one. This strategy can keep the performance slowdown of the application within 5%. vtism is designed to address the challenges of tiered memory in virtualization environment. vtism includes three core modules. First, adaptive guest-side page tracking. It installs a kernel module to track memory access patterns within the guest VM and dynamically adjust the scanning interval based on active workload intensity. It leverages shared memory to expose guest OS precise level workload information to the host kernel. Second, MGRU enhanced page hotness classifier. It enhanced the original host-side MGRU by introducing a guest-host collaborative page classification mechanism. It leverages KVM model to translate GPA to HVA, thereby enabling the integration of guest-side page access information into host MGRU framework. Third, NUMA-aware asynchronous page migration. It maintains separate promotion and demotion queue at each NUMA node. Migration tasks are scheduled to the optimal node based on the source-destination node pair, minimizing the migration latency while maintaining NUMA affinity. vtism implements asynchronous page migration during the Linux kernel work queue mechanism. Each NUMA node maintains a pair of migration queue, a promote queue for hot pages and a demotion queue for cold pages. Page promotion task is submitted to the destination node promote queue, enabling the kernel thread on the destination node to prefetch the hot pages immediately after migration. This prefetch mechanism mitigates TLB misses, and the page demotion tasks are submitted to the source node demotion queue. We compare vtism with the state-of-the-art tiered memory management, including AutoNuma, TPP, NoMan, to reflect the diversity of real-world workloads. We select 6 popular benchmarks covering key value store, graph processing, machine learning, high-performance computing, and random memory access patterns. Redis and PageRank are typical access patterns for hot data sets. vtism achieved 44% performance improvement on Redis and 27% on PageRank, outperform both AutoNuma and TPP. Graph 500 and linear are typically sparse memory access workloads. vtism also achieved 11 improvements on Graph 500, higher than TPP, but lower than NoMan. Access Bench and GUPS are representing bandwidth intensive benchmark. Both TPP and NoMan exhibit slowdown, but with performance degradation of 5% and 10%. But in contrast, vtism rely on NUMA affinity scheduling and work query binding, still get a better performance. We use the ablation study to demonstrate the effectiveness of each key component in our system. We use AutoNuma and host scan with synchronic migration as baseline, compared with fixed scan interval, adaptive page table scan, and asynchronic migration. It can improve the page tracking, page classification, and page migration, all contribute to the improvement. Thanks for listening.